So by this time, you should have logged your first attempt at Module 5, System Architecture Part 1. And the goal is to go ahead and take a few minutes to review the item analysis that will be separately recorded. So I will record in a separate screen recording the item analysis for Module 5 Architecture, System Architecture Part 1, where the first attempts are in there. And I'll also post the reconciliation. And that'll give you ample opportunity to make any quick corrections. And if you'd like to go ahead and log a first attempt, your final attempt of the Module 5 solution before the final exam next week, you can go ahead and do that. Today, we're going to take a single day to cover special topics. That's the whole part. That's the whole focus of System Architecture Part 2. And hang on just a second. Okay, so please watch for the reconciliation that we'll post in Module 5, and then go ahead and complete the reconciliation for Module 5. And then after we finish our review of special topics today, please log your first attempt of the Module 6 assessment before close of business tomorrow, which would be the study day. So officially on Tuesday and Wednesday, you'll have an opportunity to review what we cover today, and then log your first attempt of the Module 6 assessment before close of business, 11:59 p.m. on Wednesday, 23 November. That means that as we get ready for the week of final exams, you'll have a chance to engage any remaining final attempts of module assessments, retakes throughout this week, and you'll have the entire week to prepare for and engage, resubmit any solutions or assignments, that kind of thing. I will make the final exam available on the day and time of the official UVI exam schedule, but no one is required to go ahead and take it at that day and time if your other obligations during finals week allow you to flex your time and do otherwise. Regardless of what you submit and when, all students need to finish any resubmits or any assessment retakes and the final exam by 11:59 p.m. 3 December, Saturday. So if you look at the if you look at what you're doing that finals week, you have a lot of latitude to adjust as needed. Any questions about the week of finals and our expectations this week?
No.
Okay, just remember, reconcile Module 5 before Wednesday is over and log your first attempt of Module 6. So you have your study guide and special topics in the special topics folder. And essentially, as you look at the study guide for Module 6, it's only 6 pages, but then there are special topics with plenty of graphics that are short reviews, 3 pages for from Blade to Cloud, 2 pages to review something called the IO continuum. We have a special focus, 6 pages, again, lots of pictures about redundant disk arrays, RAID 0, RAID 1, and so on. We'll get into that in just a moment. And then 2 pages for the Internet of Things, IoT, right? So we have a lot of connected hardware and digital components, and that's part of our focus with special topics. So essentially what we want you to be able to do is to prescribe the best type of RAID or redundant array of independent or inexpensive disks to implement on a system for a given scenario. So as we look at special topics in terms of system architecture, everybody's familiar with this concept of a data center or the cloud. Yes? Everyone's heard?
Yeah.
Okay. And so what you're looking at are massive amounts of data storage in a data center, like a Google data center or Amazon or Facebook. They all have data centers with huge amounts of storage. And it's the reason that streaming media is possible in the first place. Well, in order to do this, basically in server systems, you have specialized arrays of hard disks. And so what we'll do is basically walk through some of this quick stuff here, and then call out some really the most important concepts, right? The most important concepts related to this. Let me update my participants list. Good morning. To those of you who are joining us in progress, please be sure to watch the early part of this recording about final obligations our last week of class together. So when you're trying your first RAID 1 mirror, it doesn't cost that much. Now, what do we talk about a RAID 1 mirror? When we're working with RAID, essentially what we're doing is we're teaming hard disks together. And there are some basic configurations that are indicated by the RAID number. That's the RAID number reflects the kind of combination or configuration of the disks. And in RAID 0, we have something called disk striping. So when you have disk striping, what you're doing is using both disks in tandem. And let's pretend that you have a 4K movie and you're storing a 4K movie that's 12 gigabytes large, not gigabits, gigabytes large. Let's say it's got lots of really cool special effects and it's 4K video, it's high resolution, it's a large file, it's 12 gigabytes, right? Not gigabits, gigabytes. So if you multiply by 8, that's actually, did we say 12? So 12 times 8 would be 96 gigabits of ones and zeros. And what a pair of RAID 0 disks would do is chunk up that movie and store one part of the movie, let's say the first chapter of the movie. Half of the first chapter would be in one disk sector in the first disk, right? And then the other half of chapter 1, the other half of chapter 1 would be on disk 2. The same thing is true of very large graphics files. What we do is we split them up and we store separate chunks of that one data file so that basically when we're playing it back, the two disks work in tandem so that there's not too much stress on any one disk. In simple terms, if you had a RAID 0 array with two disks, the read back, or when you play back the movie, it's twice as fast. If you had a third disk, it would be 3 times as fast. If you had a fourth disk, it would be 4 times as fast, and 5 times as fast if you had 5 disks, 6 times as fast with 6 disks, and so on. So it just, the more disks you have. Now there's one problem. What happens if one of those physical disks fails? Do you have a complete copy of your movie? Yes or no?
No.
No, you don't. You don't. You're missing pieces of the movie in each of the different chapters, right? So the benefit of having multiples is that you split the workload across multiple disks. It's called load balancing. And you increase the performance by multiples. So that's what you're doing with RAID 0. And the good news is you get much faster performance and much greater storage, but what you don't get is redundancy. You don't have any extra copies of the movie. So what happens is that you end up losing, if you lose any one of the physical disks, you end up losing everything. So that's the bad part about RAID 0 striping, is that even though you share the load and you don't wear out as many of your disks as fast. So when you're load balancing, you're kind of stretching the lifespan of your disk too. So you're cutting your wear and tear on the disk in halves and thirds and quarters and fifths. So you tend to stretch out the life of the disk if you share the load of the disks in multiples, right? So the only problem is if you ever lose one of those physical disks, you lose everything on that array. So there's no redundancy, there's no resilience in terms of the data, but it is wicked fast, and it does stretch out the life of a disk for quite a while because it shares the load on that disk. When you have lots of media and lots of data, RAID 0 is a good solution. Especially for media you don't need to retain copies of. Now, if you have a RAID 0 array and then you keep a backup of what's stored on there, then you're fine. You just recover the backup. So if you want ultimate performance and you're not worried about extra copies of the data, RAID 0 is what you want. Any questions about RAID 0? Any questions?
No.
RAID 1. RAID 1 is when you create multiple copies of disks, multiple copies of disk files and disk directories on each of the disks. So you have multiples of disks, but they have to be an even number of pairs. So you can only have a RAID 1 array if you have 2 disks or 4 disks or 6 disks or 8 disks. It has to be even numbers of disks. And basically, a large data file is written on each of those disks. So if we had 2 disks in a RAID 1 array, a very simple arrangement, and we had the same movie concept, a 4K movie, 12 gigabytes, 96 gigabits, we'd have chapter 1 and chapter 1, full copies on each of those disks. So when we're reading those back out, the disks can work in tandem to take turns playing back the movie. So we have redundancy, right? But there's also fault tolerance, which means there's load balancing, but then there's also fault tolerance because we have an extra copy of each chapter, and it's a complete copy of each chapter. So what we say is that the data is mirrored on each disk. Now, that's good, except if you're writing. When you're writing the movie the first time to a RAID 1 disk array, you're writing multiple copies of chapter 1 to each of the disks. So writing chapter 1 takes twice as long, 4 times as long, 6 times as long, 8 times as long, however long. You're also stretching out the wear and tear on the disks, right? But basically what you're doing is you're decreasing the capacity of your disk array. So unlike here, let's pretend that we had a 2 terabyte disk here and a 2 terabyte disk here in a RAID 0 configuration. If we combine those 2 terabyte disks, we have a 4 terabyte RAID 0 array. But that's not the case here. If we have a 2 terabyte drive 1, hard drive 1, and a 2 terabyte hard drive 2 with a RAID 1 array with 2 physical disks, we only have an array that has 2 terabytes of storage capacity. That's because every time we write something, we're writing an extra copy. So we're not actually adding the total storage capacity of each disk in that case. Does everybody understand what I'm saying here?
Yeah.
All right, so you can add disks, but you can only do it in pairs or even numbers. There's a huge, big advantage over RAID 0 in that the playback is faster as a multiple, but the write performance is a fraction of what RAID 0 would be. So RAID 0 is better at capturing huge amounts of data fast, where RAID 1 is not good at capturing huge amounts of data. But once the data is on the disks, it can play them back very fast. And there's fault tolerance. So if one physical disk drive goes bad, I still have extra copies on the other physical disk. So that's the difference between a stripe and a mirror. Disk striping is the first type of RAID configuration. It doubles the read and the write performance. RAID 1 is the next and higher level of redundant arrays of disks. The read tolerance of the read performance is just as good as RAID 0, but writing to the disk is slower. That's the only disadvantage, okay? Any questions about RAID 0 or RAID 1? Let's look at RAID 1.0. Now, you got to understand RAID 0 is not fault tolerant, which means if you lose any disk in the RAID 0 array, the whole array is done. The whole array is cooked. Everything that's stored on all the disks in the RAID 0 array is gone. So you want to keep backups, right? RAID 1.0, if you combine mirror and stripe, if you say, okay, I love this idea of striping for performance, and I also like the idea of redundancy, and you combine the two, we say that we have RAID 1.0. So it's not RAID 10. It's considered bad form for anybody to say RAID 10. It's RAID 1.0 because it's a combination of striping and mirrors. Now, in this case, you have to have a minimum of 4 physical drives. So you have to mirror and you have to have pairs. And by the time you mirror a pair, you have to have a minimum of 4 physical drives. Now, the one downside of 1.0, you get the best of both worlds, but the one key detractor from this arrangement is that essentially with a RAID 1.0 disk array, you use an awful lot of physical disks. So you cut the amount of capacity for the number of drives that you have in this RAID 1.0 array in half. So it's a bit like RAID 1, you cut your capacity in half, but you do have better performance and you do have redundancy both. So essentially, as we're looking at this example, if we had 2 terabytes each physical drives in the RAID 1 array and the RAID 1 array here, and then these were striped, the 2 RAID 1 arrays were striped, we would have a total of 4 terabytes. We'd have a total of 4 terabytes, even though we have 4 2-terabyte disks. We'd only have half the disk capacity. So instead of having 8 terabytes, we'd have 4 terabytes. But the good news is it would be very fast and it would be very redundant. And this is the type of array that you want to have if a machine is high performance and the integrity of the data is really a deal. So Google, for example, there's hundreds of millions of people that are working Google searches, and that data has to be fast and it has to work well, and you can't have data corruption. So RAID 1.0 is probably the array that's used for Google. And the thing that I want to impress on you is that it's the one that takes up the most money in terms of disk capacity. You have to buy more physical disks, but you get the best of both worlds. There is a fourth option. Any questions about 1.0?
No question.
Now, if you happen to be using a disk array to host virtual machines, and you're creating virtual hard disks for virtual machines, you always want to use RAID 1.0. You never, ever, ever want to use the poor cousin of RAID 1.0, which is RAID 5. So computer scientists came up with an alternative. They said, you know, RAID 1.0 is great, except it costs too much. Oh my gosh, you have to buy so many physical hard drives. And we don't like that. So what they wanted was a solution that would provide some redundancy, some fault tolerance, but also allow for more capacity. So in another way to put this is, you can say that RAID 5 is the worst of both worlds. It's the worst of RAID 0 and the worst of RAID 1 combined. You'll only do it if you're, well, if you don't have the money. If you're poor in terms of your budget and you have to stretch your disk capacity, and you also need some redundancy, you can use RAID 5, but RAID 5 is slow. And RAID 5 only allows you to lose one disk. So you can gain more disk space and use more of your working physical disks. And if you lose a physical drive, you can replace one of the drives. But it doesn't have the performance of 1.0. Because of the calculations that are used, there's an algorithm that's used to create the redundancy. It's called parity. There's a parity disk. One of the disks is used for parity and the other three are used for storage, like striping. So if this were a RAID 5 array, we'd have 3 2-terabyte drives. We'd have a total capacity of 6 terabytes, but we'd have a single parity disk that we can't use except for these algorithm calculations that are basically backup copies of each read and write as they're occurring. And we can, if we lose any of the 1 disks, we can rebuild those disks, but it takes forever to rebuild the disk, to replace the disk, and the performance is slow. So we neither have performance gains for RAID 1, nor do we have performance gains for RAID 0. We just have lots of capacity and there's some fault tolerance. But again, it's for people that are on a tight budget that can't afford 1.0 properly, okay? So there's a derived recovery data. It's called parity data, and it's used by an algorithm. So there's a higher load on your CPU, and there's more memory that's required from your system in order to make the RAID 5 calculations to put it on the parity drive, right? So this is an example of RAID 5. What we have are pieces, to use the movie analogy. Let's say that we have the first chapter and we break the first chapter of the movie into 3 separate pieces. We'd have each of the 3 pieces, the first part of chapter 1, the second part of chapter 1, and the third part of chapter 1 on 3 different disks. But then in the last disk, we'd have some parity data that was stored so that if we lost any one of these disks, we could recover that piece from the set. And that actually works, but it's slow. And the performance hit is really terrible. It allows you to have huge amounts of capacity. Now, if you buy a disk array and set up something called a NAS or a SAN, we'll get into that in a minute, a network attached storage or storage area network, essentially what happens is that there are new combinations of redundancy. RAID 5.0 and RAID 6.0 don't just, after 25 years of working this in industry and having built data centers myself, I would never use RAID 5.0, never use RAID 6.0, never use striped versions of a RAID 5 array. I just wouldn't use RAID 5, period. if you're gonna spend money on a data center, you just have to make sure you have budget for physical disks. Because you're going to the trouble to build a data center in the first place. Who would build a data center and not have enough money for decent hard disks and decent quantities of hard disks? I'm just asking the question, right? And wouldn't you have spares? Now you can configure spares so that they automatically replace in the middle of an array. There are all sorts of extra features for RAID. But essentially, I want you to know about RAID 0, RAID 1, RAID 1.0, and the poor cousin of RAID 1.0, RAID 5. I want you to know that RAID 5 is the worst of RAID 0 and the worst of RAID 1, and you would only use it if you needed lots of capacity and some kind of redundancy, but you just couldn't afford to do RAID 1.0. Any questions about the 4 types of RAID? Any questions? Now, I do need to tell you about 3 different ways to work these arrays. So when you have so many disks, can everybody see the picture here?
Yeah.
Yes.
Okay, so we have a computer server chassis, and this is probably a 2U or a 3U unit. So when you go into a data center, you have these compartments, and if it's the thinnest compartment, they call that a pizza box. It's about the width of a pizza box. That's a 1U unit. If you take 2 pizza boxes and stack them on top of each other, it takes up 2 of the rack units in the system. And if this was an older style server and these were 3.5-inch traditional hard drives, that would actually be 3 or 4U. But these are sideways hard drives. This is nothing but hard drives. And out the back end of this is a special connector that runs in parallel, not in series. It's called SCSI, Small Computer Systems Interface. Now, SCSI has been around a long time. But basically, this whole chassis can connect to a server, to the motherboard of the server with that parallel cable, and the parallel cable can run about 3 feet. That's it, 3 feet. This type of massive storage that's directly attached to a server is called direct attached storage, or DAS. Okay, and there's a link, so you can check out DAS. Now, there's another way to do this. So basically, if you have a server and then you have these direct attached storage units, you can have up to 127 disks connected to a single server with direct attached storage. So you can have lots of direct attached storage and then put them on the racks. They all look like this. Now, what's network attached storage? Instead of having the parallel cable that's only 3 or 4 feet that connects directly to the server, so it's still connected in through the motherboard and the south bridge, or if there's a disk controller that's SCSI, it's north bridge, right? If you don't have a direct connection to the motherboard of a server, you can put this entire thing on the network, and you have network cards out the back, and you pair the network cards together for greater speed. This is called network attached storage. And network attached storage has been around a very long time. And network attached storage means that you can treat a hard disk as if it were connected locally, except it's not. It's connected across the network. And whenever you connect a disk like this, in order to use the disk, it has to be assigned a logical unit number, or a LUN. I know it looks like LUN, but it's pronounced LUN. And the first LUN that is set up for a disk array that's connected to the networks is LUN 0. Now, one thing about network attached storage is that it's very old technology, but very stable technology. And there are ways to secure it to some extent, even though networks tend to be exposed. So the network security is okay, but not ideal. It's not as good as direct attached storage. So in terms of file security, direct attached storage is better than network security because networks can get hacked, right? But one of the cool things about network attached storage is that you can create huge arrays that hundreds or even thousands of users can take advantage of. The other thing that you want to understand about network attached storage is that it's called file level access. That means that each system that's accessing it across the network has to have an actively running file system, or you can't access the data. What are we saying? Well, you have to create directories, and there has to be a formatted file system like NTFS or FAT, which is something that we go into quite a bit in our operating systems class. But basically, it's file level access for NAS, okay? So you can have huge disks, then you can have hundreds of disks that all make up a terabyte, which means that, so if you have 2 terabyte physical hard disks, right? And then you have a store of 16, you can have eight RAID 0 arrays with 2 terabyte physical hard disks, and that gives you 16 terabytes on a storage area on a network attached storage, right? So that's one thing that you have to remember. There's a special file system that was developed in the 80s that's still around. It's called Network File System, NFS, and it's one of the ways that you connect to a NAS. So any questions about network attached storage? Sometime later, they discovered that network attached storage has all sorts of limitations. For starters, it's file level access. So you have to run certain protocols on your operating systems in order to take advantage of the hardware. You have to run server message block across the network, and that tends to be very vulnerable. Or you have to run FTP across the network, or HTTP, right? There's another common internet file system called CIFS, right? Common Internet File System. This is something that you see in some Linux systems, and then of course there's Apple. There's Apple talk. In any case, the thing that you need to understand is that one of the vulnerabilities of a NAS is that all of the things that make a file system vulnerable become that much more vulnerable on a network. Now, it is common for a network attached storage to outperform a traditional file server, because if you're facing a case where a single file has to be read by multiple users simultaneously, think of a computer lab, right? If you had direct attached storage or a storage area network, we'll talk about SANs in just a second, the NAS will outperform a traditional file server because it allows multiple access simultaneously on the file system level. You can set up a NAS on a common wireless router. So one of the things you can do is have like an appliance with some disks and then connect it to a port on your Wi-Fi router, and you can have local storage available. And they're usually advertised as media servers or, network storage. So that's another thing that you see too, is that there's a lot of NAS used with home Wi-Fi routers to allow people to add extra storage for their homes if they want to have extra like movies and music and that kind of thing. Any questions about NAS?
No.
Storage area networks. So not long after they started with NAS, it wasn't but a few years, and they discovered that there were some limitations to file level access. And what they wanted was the best of both worlds. they wanted direct access to the disk sectors. So we'd call that sector level access, right? We want our hard disks on the network to be, we want them to appear to be locally attached, like direct access, direct attached storage, but they're still on the network. And what they came up with was an innovation known as SAN. A storage area network allows the network store to pretend to be a physical hard disk as if it were directly attached. Now, what that allows us to do is it allows us to create servers that don't have any disks. They're diskless servers. So we have a storage area network with very fast disk arrays, and they're redundant. And we have multiple copies of that SAN, so there's redundancy. And so the disks are redundant, and then the SANs themselves are redundant. They're implemented in clusters, so you'd have more than one storage area network, and they're mirror copies of each other. You would do that in places where the data access is very fast, you know, again, online systems and cloud storage, right? So what happens is that the servers can be mounted into a blade. So this is called a blade server. And it looks like a video card. So what am I saying? If you can create a storage area network where the disks act as if they were physically available and connected locally, but it's done across a network, what we have is a storage area network, and the storage is disk sector, not file level. So it's block level access down to the disk sector or block. We say hard drive block, we mean the disk sector, the physical, right? The physical part. So the array on the network looks and feels and reacts, it connects just like the direct attached storage, except it's on the network and it's huge and it's very fast, much faster than NAS. So, and it looks like it's a physical hard disk that's connected. It's not a file level connection, it's a block level connection. And we still use loons, right? So we still create loons that machines can connect to, but the main advantage of having a storage area network is this. I can now create servers where I have a simple card like a video, it looks like a video controller, a graphics controller. It looks like a graphics adapter for a gaming system. It's a single card or a blade, and what's mounted on there is CPU, RAM, and a data bus. So I don't have to have a complete rack taken up for one server. I can put multiple servers on a single rack. So if I have 12 blades on a single rack, now I have 12 servers in a single space on the rack. So now I can create multiples of the servers. That's a huge advantage because it means now I can create many servers physically. I can run them together in what's called a cluster so that they're redundant. And all of them can share this storage area network. So if I have to, I can move servers or recreate servers very fast. So the innovation between the SAN and a blade server allows physically for IT professionals to do much more with their data centers. The thing that I want you to understand is the difference between these two types, right? So there's a kind of a hand-drawn graphic here that I'd like you to take advantage of. And here, you know, network attached storage is older protocol, it's file-based access. So all of the things you need to know about network attached storage versus storage area network, right, are all together in one simple graphic. So it's this foundation that allow the other special topics to happen. If we didn't have this kind of progression in our data centers where we could build out huge data centers with blade servers and storage area networks, we couldn't connect, there wouldn't be any data on the back end in the cloud to connect our smart devices to. So the Internet of Things phenomenon that's happening right now would never be a reality, right? The other thing too is that one of the things that I've told you before is that the further you get away from the CPU, the slower it gets. So when you have cloud storage, it's that much slower than network storage, local network storage. But on the other end of it is a huge data center with lots and lots of storage. Now here's the special topic that finishes the review we're talking about when it comes to blades. This is an example of a blade server. So I have 2, 4, 6, 8, 10, 12, 14. I have 14 servers in just one half of this blade server. Is that right? 2, 4, 6, 8, 10, 12, 14, 16. I have 32 servers in this one machine right here. 32 servers, each with multiple CPUs and hundreds of gigabytes of RAM. And there's a huge data bus on the back end of this. So I have 32 servers. Each of these are connecting to a SAN. So when they boot up and they have to store files, they're storing them directly in the storage area network on the SAN. But if my server blows up, I just pull the blade and replace the blade, right? That's called a diskless server. So that's where this other special topic comes from. It doesn't take a lot of money to set up a data center, but here's an example of what that blade server looks like up close. All the RAM modules, the CPU slots, and then on the back end, you have this huge input-output connector, 25 gigabytes of Ethernet connection, right, out the backside. Very low cost. It's what makes the cloud and all of these things possible. Speaking of cloud computing, the one thing I want you to understand is that there's 3 kinds of cloud. There's a quick review of each different type of cloud. There's infrastructure as a service. That's when a cloud provider gives you all of the hardware. There's platform as a service. That's where they give you all of the hardware and the operating systems. And then there's software as a service, where they do the hardware and the operating systems, and they create the applications that you use through the cloud. So all you're interacting with is an application in the cloud, as opposed to platform as a service, where you're interacting with the operating system in the cloud, versus infrastructure as a service, where you're connecting to the hardware in the cloud, and you're configuring your own servers and your own systems, and you decide what operating systems you want to build into there. So infrastructure as a service is the most work, and it's the most basic provision. It's the most basic and lowest cost. They just give you the box and the hardware. They give you this. And it's up to you to decide whether you're going to put Linux on it, or you're going to put Windows on it. You're going to put an Apple file system on it because you work with Apple stuff. It's all up to you. Platform as a service, they set up the servers with Windows or with Linux. And what you're doing is logging into the servers, and then you're creating your applications after you have access to the operating system. In this case, you're not worried about the hardware or the operating system. You're just working with developers, and they create the application, and it runs as an app on your devices. So those are the 3 different kinds of cloud services, the way they are right now. And there are different examples, and we explain like all the different types. One thing I would advise is that I don't think that anyone in the Virgin Islands personally should be using complete cloud solutions, because if we lose our internet, you can't get to it. What we really need is hybrid, where we have some local data center and then we have some cloud stuff. That's what I would advocate for anybody. So that's all we have time to review, but basically I've walked through a number of the special topics, and that's what each of these sections in the study guide points to. So all I've done is called those out. Take a little bit of time to look at the virtual machine section in Student Learning Objective E. Are there any questions before we finish? Okay, I'm going to post this recording right away. And if you need any assistance or with retakes for the assessments, or to get the final round of assignments and solutions done, there are no assignments or solutions for Module 6. It's just content. That's it.
When is the retake for Module 5?
I'm going to be putting the retake for Module 5 out either later today or tomorrow. And you'll have all next week along with Module 6.
Okay, thank you.